YouTube change their buttons, like the screens, I guess to match like the mobile buttons. Look down there. Yeah, it's fine. Cool. And I think today, main goal, finish up project 2 or submit it. Or wait, what's our schedule? That would help. All right, we'll go calendar, due dates. All right, so we just turned in project 2 somewhere. Where's project 2? Submit project 2 yesterday. Okay. There we go. And now we're into module 3. There we go. Cool. Were there any like leftover questions about module 2? Yeah.
There's like one of the last ones, there's like a Z thing. Since Z equals 3, I think.
In the homework or in the project?
I was wondering what that did.
Do you know where that Z equals 3? Is it a...
We were doing the R thing. Oh yeah, Z order.
Z order? Oh, this one?
Yeah.
Oh, so you can manually place, like when you put a line on a graph, they're all like drawn on top of each other. And so whenever you specify the Z order, you can say like, do you want it to go up front? Do you want it to go in the back? So you can manually say like, all right, there are, on this one, I mean, I've got over 100 lines on here. So I'm saying like, all right, the third thing on here should be this error bar. That's what that Z order, yeah. So it's like the Z out of, out of plane order. Yeah, that's a good question. Did you try playing around with it, like changing it? Okay, yeah, that makes sense. Because it's probably, yeah. Let's go kernel, restart, run all. Take a second to catch up. Yeah, if it's 1, I think that's all the way in the back. And then 2, now the dots are up front, but the lines are behind, like the error bars are behind there. And then 3 was what we had it at. And then after that, it's in front of everything already. Yeah, so 1, 2, 3. And I think that's why, because we have like plot number 1, plot number 2, and then this is our third plot. So if we say Z order 3, we're like forcing the dots, these circles, and the error bars to be up front.
Wait, can I ask you a question?
Yeah.
I was getting an error yesterday with the, I was getting an error, but it would still run. I can't believe.
So sometimes there are like warnings where it looks like an error. It's a big kind of red or pink box, but it's just saying like, hey, watch out. Like it,
Oh, okay.
I tried to do what you told me to, but it's not really, but it's probably not what you expect.
And then I also had to like take out one of the lines that he had and like change it. That was getting my like.
Yeah, like I know last time we were taking a look at this format.
Yeah, that was
Okay. And that one, this one gives you an actual error. Like it won't run because it can't convert that time series to ISO. So that one we can comment out, and then no error. And then let's see, I'm trying to think of where there would be a warning, but stuff would still run. I don't know. Because most of this is kind of like building data, summing it up. Okay. Yeah, and last time, like end of class, I was showing like how to actually quantify error in the model of like, hey, we have a prediction, and for Monte Carlo, at least in this case, like the best prediction that we can make is sort of the average. Like if we take any one of those given lines, it's not really representative of like what we think will happen. So the average is sort of like our prediction. The error bars are how precise our prediction is. So it's not error in the sense of like this is how much error. It's just like this is the range of values where we would expect the price to be based on our prediction. So if we take the actual like opening price, subtract our model price and divide by that standard deviation, it tells us like, are we within one standard deviation or are we within two standard, like 1 to 2. And here at the very beginning, it's like 2.5. But by the end, we're within like a quarter of a standard deviation. So it's a very accurate model. Like we're predicting the prices, but it is not a precise model. Like very much, the longer we try to make a prediction, the bigger our error bars get, so the less precise the model is. Just using that engineer speak of like accuracy, precision. Very accurate, very not precise. Very much not a precise model. Which makes sense, because if we're saying this is a random walk, the stock market, then there's no way to have like a precise prediction. Like we have to have some kind of error as we walk along each day. Did you find it? Yeah? You want me to take a look? Or anything, any other questions on like homework too? Or is that one? Maybe. Yeah.
I think the homework too. For the last problem, I just didn't know really like care about the kilograms time travel. But I did everything else.
So that is, let's see. I got an error somewhere up here.
Also, why if you hit run all, does it not generate all the graphs?
If it runs into an error, then it stops. So that's what happened to me. It went through the first 9, but then when it got to this one, it could not do that one, this cell. So I can try it again. Might hit another error. So this time it generated like all of my graphs because, so if it runs into an error, it just stops and then waits for you to figure out what's next.
Maybe it was because of that warning, but when I was trying to run all, it wouldn't generate all the graphs yesterday, but if I like just went through each cell and
Yeah, if you run each one.
it would generate the graphs.
I think a lot of times warnings
Or maybe it was
continue, like it lets it continue to run. So I'm trying to.
It said every cell was executed too, but it wouldn't do the graph unless I retyped it.
Yeah. That's weird. It should run. Okay, but so with this last one, we have, this is a like classic kind of propagation of error analysis, which is if you're doing senior design, this is exactly what you should be doing, especially at this stage where you're saying like, all right, we can buy these parts. We know that the parts have some tolerance. How does that tolerance like propagate into how effective your design will be? So you might have 10 different parts, 10 different tolerances. All of them have to add up to like whatever, a given power output or a given like stress state or force, like applied load. So this is like simplest case where we're just considering the radius of a rod, and so for one given radius, it will have a buckling load at it, like if it's a certain length. So we're trying to figure out how tall can we make this structure if the load on every rod is 1,000 kilograms divided by 100. So each one is holding a 10 kilogram load. I mean, it might not be, like maybe it's not exactly that, but that's kind of what we're imagining. There's 1,000 kilograms with 100 kind of support structures around it. So that comes up here because when I make my like critical buckling loads based on the radius, let's do this. If I say default is length is 5, one way I could think about it is like if I assume that it's a normal distribution, the mean minus 2 standard deviations is kind of describing the lower bound of my 2.5%. That's like, if we think of it as a histogram, there's 2.5% that's going to be below that mean in 2 standard deviations, and 2.5% above that mean plus 2 standard deviations. So in this case, 5 meter tall structure, the 2.5% will fail below 33.9 newtons based on the radii that I created. And so if I want that to be 10 kilograms, then it's got to be more than, this number should be 98 or more. And that's where that 1,000 kilogram structure, like we need to compare somehow the stats of lower bound with 10 kilograms on each rad. So guess and check I could do, like, all right, well, let me make it 2. And now it's 211. So that's too short. So I can make it taller, but you can kind of work my way there. But definitely put this in your pocket, do some senior design, throw some Monte Carlo in there. It's always like a very impressive but very easy to do calculation, because it's a textbook calculation. Like this formula is something you can look up in a table, and then throwing random numbers at it gives you like a propagation of uncertainty. Yeah.
Is Monte Carlo better than like, or typically more accurate than just like doing it by partial differential equations?
So partial differential equations, that would be stuff like if you're doing CFD or FEA, those are solving partial differential equations where you have boundary conditions, you know the physics connecting the boundary conditions, but you don't know what's happening in between. So you create these differential equations, you solve for like, what is the shape of this thing, what's the stress state, what's the strain, but all of that is very much like, you'll get one answer, and that's the answer. The benefit of Monte Carlo is that you can say, all right, I know my boundary conditions are, if it's temperature, I know it's somewhere between 90 and 100 on this side, and I know on this side it's somewhere between 10 and 20. So I could look at I could solve that differential equation and figure out what is all the different temperatures across this rod with varying temperatures based on like averages and standard deviations. So it's a different approach. In terms of accuracy, solving a PDE is always way more accurate than Monte Carlo because there's only ever one answer. Like you'll always converge to like one solution, but sometimes it's not giving you the information that you want because it's only a single set of boundary conditions and a single set of material parameters. So if you're trying to figure out like how much does everything change, that's where Monte Carlo would come in. Cool. Yeah, speaking of differential equations, that's our next step. So we're going to look at least to start, initial value problems. So looking at derivatives and integrals with like computational methods. That's what this this notebook's all about. Usually the thing that people run into, we'll go into the homework, then I'll show you one little thing that comes up. So first thing that you're asked to do in the homework based on the part 1, based on that first reading, is use the projectile coordinates that you saved from the reading. So if you skip that part, then you don't have this file. So that's the first step, is like we should do this projectile coordinates save kind of thing. And we can either save it into our data folder or we can save it into our like current directory. So back here in part 1, I'm speed running through it a little bit. We're going to import some widgets. But here what we're doing is importing a video and then looking at it frame by frame. So we can actually track the motion we're doing it manually. There are automated methods to like figure out where is this ball most likely based on, but it's good to try it manually to start, just to see like how would you tell a computer how to do it. And so right now, first time we look at this, it's a single image. And when we have this single image, goal is click on the 0, 10, 20, 30. So we're trying to get an average number for like how many pixels is 10 centimeters. So we're gonna click on each vertical step. So I'll click here, here. And it doesn't matter like if I follow one like vertical line, as long as I'm clicking on each horizontal line. After you click, every time you click on the image, this variable called coords, this thing gets overwritten like every time you run one of these cells, not every cell, but this line that you see here where it says coords is an empty bracket, that resets whatever I clicked on. So if I run this again, all my coordinates are gone. It's not a big deal. I can click on everything again. But if I want to at least say like, all right, I like these coordinates, I think they're, or I guess I could check to see, does the number make sense? So in this case, it says 53.3 pixels every 10 centimeters. That's kind of my conversion factor. At least that's what I get. If you do it, you'll get a different number because we have different clicking. And so if I like those numbers, I could take all this and paste it in there just to kind of like save my work, at least like so it doesn't go away the next time I try to run it. That one's just a kind of a notebook trick of like, how do I create like a reproducible step? If I go through and rerun this notebook, will I get the same values there? All right, now that I have a conversion factor, anywhere I click on the graph, if they're 53 pixels apart, I know that they're 10 centimeters apart. If it's some fraction of that, then I know exactly how far. So now I can go through frame by frame and click on where the ball is and get like how many centimeters in each frame the thing moved. So right now it's up at the top, so I'll click up here. I'll scroll up, go to the next frame, and then it's over here. Oh, I gotta zoom out a little.
Can you click outside of the bounds of the ball?
Can you click outside the bounds?
Yeah, because like you see how the ball is like kind of outside of that 0 centimeter.
Oh, yeah, you can click anywhere. So in the image, it doesn't care if you click like up here or way down here, but if you click outside the image, then it's done. I'm trying to zoom out enough that I can see the, yeah.
Does it only say one click for each time you click it? Like if you have something like this, then can you just click again and it overrides it for that slide?
Every click gets, so let's take a look at like what we're doing. Image, catch, click.
It's kind of frame, wouldn't it, when we set one?
No, because every time you click on the image, it'll grab you another one. So I'm trying to find, here we go. So our main like function that's grabbing this information is this onClick, and it takes that coords and appends ix, iy. So every time you click, it's going to append another value onto it.
So what if you mess up?
If you mess up, there's two things we can do. So let's take a look at. So I'll click through, and then I'll mess up, because it's not a big deal. I think I just messed up anyway.
Would there be a way to make it so that it can only have one input per frame and it just takes your most recent?
For every frame? Maybe. What you could do, you could write your own function where like every index, like coords is a pre-written, like it's an array that has whatever those 25 values that we're trying to click on. And so on frame 59, it is row 12. And so every time you click, it'll just update row number 12 until you move to the next frame. Yeah. Yeah, that would be cool. I'm just going through this partly for the video, also just so we get like a solid data set that we can look at. All right, cool. And I'm gonna get rid of all that. All right, so I already have like a problem in mind where the second row is none and none, because I must have like clicked within the figure but outside the image. Not a big deal, but it's there. But let's take a look at, all right, so I gotta get rid of this none and none to start. And I could just redo the clicking, but I'm gonna show you how to manually get rid of some stuff. So I don't want this row. I'm just gonna delete it. And now that row is no longer going to give me an error. And then when I plot it, how does this look for my plot? Does it look we have some outliers. Are they real, or do you think that that was me being an ogre, not using the mouse correctly? That I that I clicked somewhere wrong, right? Like something happened. So let's track down those things. So looking in here, at least for that Y, there's like one big jump in the Y over here, and it looks like it's index number 26. So I can come back up, and sure enough, I have like a 864 and 887, kind of my X values, and my Y is like 512, 550, and then 250. Like, all right, well, I don't want that 250. I think that one's wrong. So let's come back up here, and I'll delete that one. And now, let's see if it's any better. So my Y looks a little better. Let's check X. X also has like, it was increasing roughly in a straight line, but then something happened at index 23. So I'll go back up, look at a jump at the 23rd line. So somewhere in here. I think this one's no good, because it's, if I'm looking along here, I've got 600, 630, 650, 680, 700, 720, and then all of a sudden a 900. All right, there's something wrong with that one. Let's get rid of that. Now it's pretty smooth. It looks like somewhere back here in the beginning, there's like some error in how I was clicking. I think the initial startup looks a little weird, but we could leave it for now if we want. And look at that. Now I've got like a nice projectile motion kind of plot. Like my x-axis is increasing constant speed, and meanwhile I'm falling faster and faster as time moves on. The dots are getting further apart as I fall down faster. Yeah, so we can mess it up. Part of doing it on a computer is that it's easy to go back and edit and change things. I could even rerun it and just grab those first two coordinates and then see, like, all right, let me zoom in and get those better honed in or something. But I think this is good. So we'll take some derivatives. One of the things that we didn't explicitly like define until now was like how much time passed in between each one. This camera was recording at 60 frames per second, so every frame is 1/60th of a second. So we're saying, like, if we say delta y times 60, it's saying that we had that many centimeters in 1/60th of a second. And look at that. Acceleration 9.8. It's pretty good. Not bad. And then acceleration x should be 0. It should be a constant speed, but it won't be exactly. Since we look at like 5 sig figs. Whoa, no. 14, yeah. So that one, if it's not 10, so I've seen numbers anywhere from like 9.5 up to like 10.5. All those are within kind of clicking error, and like it's fine. If it's a number like 14 or 20 or something like that, there's probably something in the, it's probably like the gap line, like how you, so my number for gap lines was like 53. 53? Okay. Or maybe there was a frame, maybe down here. Like if these, there might be like 2 dots on top of each other, or sometimes there are missing, like if 2 of these are missing, the assumption is that, at least based on this analysis, is that every dot is 1/60th of a second away. So if you're missing dots anywhere along there, it's still assuming it's 1/60th of a second. So those are kind of the main. So let's try that out. If I come back up here and I say, let's get rid of, yeah, I'll just delete it. I can always redo it. I'm going to get rid of 2 data points in here, just so you can see like what does it look like if it's missing. And there, roughly, it looks like there's something gone. And now I'll do the same acceleration. Oh, I still get like 10.6, which is not bad. I was expecting it to be much higher than that. I think I just nailed it that first time that I happened to be like really close. I don't think I've ever had acceleration 0 along the x-axis. That's really like unnervingly close. It seems wrong. It seems wrong that it could be like that good. I feel like I must be doing something weird. All right, so connecting it back to the homework, like doing that first homework problem, we're gonna save t, x, and y all into a file called projectile chords. Default place that I'm saving it is in that data folder. You can also just save it right into your current folder. Just say // or even just get rid of that dot and just say save as that save z projectile chords, and it'll save that like homework file that you're looking for. So we could just do this. Save that. And now when I go into homework 1 and paste this in, it loads up my t, x, and y from that NPZ coords. And here's like y moving, then I could even look at like x and y. But I've got all that information. Now it's in my homework folder. It's not just in that last notebook. And this is a nice way to like get your analysis from one spot to another. Like save it as a file and then load it up in another program. And because we're using NumPy, it makes sense to use this save z, because that'll save like a nice, like it saves a really small compressed file, and you don't lose any precision in your floating point numbers. Like whatever the file was saved in the computer, that floating point number is being like loaded back up into your memory in the next notebook or Python file or whatever else you want to use. And this catch motion, this is also really helpful. I know I talked about senior design earlier. This is also a super helpful senior design method of like, you can see something happening. If you can see it happen, you can take a video of it, literally like on your phone. It does not matter what sort of recording equipment you have. Figure out the frame rate of like how fast you were recording. Usually phones are like 33 frames per second, something like 33, 32, but you can look it up like in the video. It has that information. And now you can track motion or track like changes. And you have time and position in a quantifiable way with just like video images. And you can use the same kind of analysis there for, again, like any kind of senior design. This is how fluid flow is sometimes measured with particle image velocimetry. Like track a particle as it moves across your screen, and you know how wide the screen is, so you know how fast the fluid's flowing. And then in solid mechanics, like if you're looking at bending and stretching or compression, you can get strain across a surface and look at, it's called digital image correlation at that point. It's like, how do we track what the displacements of this deforming object? All sorts of cool stuff that you can do when you start getting like images into the computer. All right, today was more of like a long tour sort of thing, but yeah.
So saving the file like that, is that gonna like save even if like you close, you open it and everything?
Yeah, so now if I go File and Open, this projectile coords, it's in my folder for that homework 3, for module 3. And it's just, it will be there every time I log into NanoHub Jupyter. So it's there forever. Well, until you say like delete, you want to clear it out. Or you can overwrite it.
And if you like opened up a catch motion and you reran it, would it like rerun it if you like change more coordinates?
Yeah, if I go back and rerun, this is going to just overwrite whatever is in that file. So if I change things and then write it again, it'll create like a new projectile coords. Or you could have different versions, like trial 1, trial 2, trial 3. But we could even like download the file and like save it. Just like keep it, like this is mine. I want to save it forever. It's not a very interesting looking file because it's all binary stuff. And if you try to click on it, it's going to say it doesn't know how to deal with it. But Python knows how to deal with it. NPZ files, they're easy to load into Python, but hard to look at because it's like binary stuff. Good. Anything else working on? be done with the, did you do design reviews already for oral 1? Or is it coming up?
I don't really think it was a design review. Like, there's one at all one
The presentation? Oh, okay. Felt like more of a design review with just one team, one professor, at least when I was doing it. Coming up today, all right.
Were you at?
Okay, all right, I'll see you soon. 2:03. The time?
Yeah, that's what it said.
Okay, yeah, we'll be late, so everything went like over schedule last time. And yeah, I don't know how to make it shorter.
15 minutes is not a lot.
It's so short. I mean, logistically, I get that that's what is supposed to be scheduled to fit into that 2-hour block of senior design time, but it's not enough time.
I think that's why I was really do design review, because it was like, you have all of these expectations for us to present to you what we've done. So that takes time.
Yeah, no, it takes a lot of time to prepare, present, review, like consider. Cool.
I have a question. Do you know how to get certain like modules into the Jupyter? It's for a different class, but I want to use
Yeah.
are like a thing for it.
So like you have a NanoHub account.
I was trying to get like image,
Oh. Like you can just like load up Jupyter. Like we're doing like a specific Jupyter that puts a whole bunch of notebooks in there. It's coming slowly. And if I load up this Jupyter, it shows me like, hey, there's comp mech, there's a dynamics folder, there's also like data and stuff, but I can build whatever things I want in here. So if I wanted to, I could upload a whole folder full of stuff that I'm trying to work on, and then use Jupyter from there.
so you can figure out like the gaps in modules.
Yeah. Or the other way is, oh wait. Oh, Coop. Like this data-driven decisions was a class that I taught last spring and last summer. I could grab this whole GitHub repository that has like notebooks and stuff in it, and README files, and then come over here. I'm gonna make a new terminal. Say git clone. And cloning like makes a copy of whatever like repository you have. Like even if you fork our current class repository, you could clone it into this Jupyter, then you'd have the same thing. And now in my home folder, I've got that data-driven decisions like work. So if someone's hosting like module stuff in GitHub, you can like grab it all, copy it into your own. Or you can manually kind of upload things one at a time, or folders at a time. All right, thanks a lot.